Okay, chapter 4 is going to be lots of examples. So we're going to look at several cases, and each of them we will use some of the at-risk functionality that we've already seen, and then we'll use them in different ways. So it's more of an examples chapter, and in the process of discussing those examples, we'll also look at some very important concepts like copular functions and correlation and things like that. Okay, the first case is going to be drug development, where we have a new drug from a pharmaceutical company, and it has to go through several phases to registration, and each phase the project may fail or succeed, and the success or failure we can simulate using a Bernoulli distribution. And then at each stage it's going to there's going to be a cost involved, and the cost again is an uncertain variable, so we're going to use a PERT distribution to simulate the cost. And then once you reach the final stage of registration, and after registration, okay, the net present value of all the profits that you'll make from that drug, okay, so that is after registration. And again, we're going to be simulating that, and then we take the time in each of those also will be simulated, and then we will compute a net present value of all the different costs in different phases. Okay, okay. Once the phase fails, that's it. After that, there is no phases after that. But so so you need to model it in a proper way, that the costs are simulated only if the previous phase is a success, and then we do a net present value and then run the simulation. So that's your case one. Then the second case is collateralized debt obligations. Again, we talked about this in an early introductory videos, where we are talking about correlation between different input variables, and if we don't consider the correlation, we'll end up with completely unreliable results. So we're going to use the outcome of, so we're going to look at the portfolio, right? So whether the portfolio will default or not is going to be simulated using Bernoulli distribution. So now if you have two or three different, we're going to be looking at an example with just two CDOs. So what is the relationship between the two? Okay, take that back. What is the relationship between the the assets inside a CDO? Okay, so if are they independent of each other? Okay, so that means there is no correlation. So if they are correlated, so we're going to be looking at a copular function for that, and then we'll run sensitivity with risks in table using different levels of correlation. What if there are no correlation? What if there is mild correlation, say 0.1 or something? What is if it is fairly correlated, 0.5? What if they are very highly correlated, say 0.8, 0.9, and things like that? So that will be our case 2. Case 3 is cockpit system failure case. Here again, we have a cockpit system with several components, say like 30, 40 components, and each of them has a mean time before failure. Okay, so we use that to simulate when a particular component will fail, and we use exponential distribution for that. And then we look at, okay, when will the first failure occur? Because when the first failure occurs, the whole system fails, right? And using that first failure, then we run the simulation and see what is the probability that the first failure will occur within 1 hour. First failure will occur within 2 hours. First failure will occur within 3 hours, and so on. So with that information, then we can come up with a maintenance plan. Now, here again, we have to be very careful, because these components may not all be independent of each other. Some components may be related to each other in terms of when they fail. So the correlation among these components need to be considered, and we will look at, so in this example we're going to look at just not a copular function but a correlation matrix. The fourth case is home prices from several cities, and here we're going to have we're going to fit probability distribution for change in home price in each of the cities. So you have like 4 or 5 cities, 4 cities I think, and you look at the change in price in each time period, and then we will incorporate a copular function. And once again we talked about this. So prices from different cities, okay, like price change in Boston versus price change in Chicago and Los Angeles. Now one may assume that they are not related, but that's not the case. Okay? They are in a way, because we have a nationalized financial system, and there is correlation. So how do we incorporate those? So that's case number 4. And then we look at some theoretical concepts. So if you have empirical data, so far we've been assuming certain correlations to come up with the correlation matrix or copular function. So if you have empirical data, now how do you fit a copular function to the empirical data? So we look at that. And then we will look at regression models. Okay, so this is kind of a different kind of topic. So we look at regression model. Then if you have not a large enough sample, we can use bootstrapping method to generate more samples and run simulation. So we look at simple regression where we have only one x variable, and we'll have multiple regression where we have several independent variables. And then we look at what is called envelope method. So envelope method is one way of trying to relate one input variable to another. So in the case of Facebook example, you'll see that the revenue growth, which is an uncertain input variable, and R&D cost, okay, that's also uncertain random input variables. So in the examples that we've seen so far, we have assumed that these two are unrelated. But is that reasonable? Now, if you spend more on R&D, you're probably going to have more in revenue. So these are related, and we will look at what the envelope. We already looked at copula and all that. So here is another method, an envelope method, where you simulate one variable. Okay, so for example here, the R&D expense. So you simulate R&D expense, and based on the simulated value of the R&D expense, you plug that in to a different envelope, or it's kind of a function, envelope function, and that envelope function parameters are determined by the simulated value of the R&D expense, and from that you simulate your revenue growth. So it's another way of, instead of correlations, are using an envelope method.